Hi everyone, today's video is going to look at acids and bases and specifically definitions and the pH scale. So when we think about defining an acid, the Bronsted-Lowry definitions of acids and bases are that an acid is a species that donates a proton or an H+ ion, and a base is a species that accepts a proton. And acids and bases must react in pairs. One partner acts as the acid, the other acts as the base. So for example, we could take HCl and react it with NH3. The HCl acts as the acid, donating its proton to the NH3, which acts as the base by accepting it. And this forms the NH4+, Cl-, ammonium chloride salt. Similarly, if we took sulfuric acid and nitric acid, species that we naturally think of as being acids, if we react them together, one acts as an acid, one acts as a base. The sulfuric acid is a slightly stronger acid than the nitric acid is, and so the sulfuric acid donates a proton, acting as a base, to the nitric acid, which is acting here as a base and accepts that proton. And so we end up forming the H2NO3+ ion and the HSO4- ion. Now these species on the right hand side also have names, so while we can say that the H2SO4 is an acid and the HNO3 here is acting as the base, the H2NO3+ is acting as the conjugate acid, and the HSO4- is what we call the conjugate base. The H2NO3 is the species that has accepted the proton, and so in order to get back to the neutral state, imagine the reaction going in the opposite direction, it would have to donate the proton. The HSO4 was the species originally that had given away the proton in order to make that species, and so in order to get back to its neutral state, it would have to act as a base and accept a proton. And water-soluble bases are known as alkalis. These produce OH- ions, hydroxide ions, in aqueous solution. So all alkalis are bases, but not all bases are alkalis. Now water can act as either an acid or a base. So for example, we can take water and react it with ammonia. In this case, the water is acting as the acid, the ammonia is acting as the base. So the water donates a proton, and we end up forming this ammonium hydroxide salt. But water can also act as a base. So if we have water reacting with sulfuric acid, well now the sulfuric acid is the acid, donating a proton to the water, which accepts it, acting as a base. And when the H2O molecule accepts an H+ ion, we end up forming this H3O+ ion, and this has a special name. It's called the oxonium ion or the hydroxonium ion. And if we have a species like this, like water, that can act as both an acid and a base, it's called an amphoteric species. Now protons never just exist as H+ ions on their own in aqueous solution. It's important to realise this. Because they're so small, it's essentially just a proton, there's no electrons. The diameter of this is about 10 to the minus 15 meters, as opposed to 10 to the minus 10 for other positively charged ions. And so because it's so small and has a positive charge, it has a really intense electric field, and we can say it has a really high charge density. And this gives rise to a whole host of different and unusual properties compared to other positive ions. One of the most striking differences is in the way that protons move in aqueous solution. So other positively charged ions, for example metal ions, the way that they move in a solution when we think about them conducting is they physically migrate, they physically move through the solution. However, protons don't do this because they're so small. They actually hop from one water molecule to the next. So there's actually no physical movement of that first H3O+ ion. It doesn't physically move. A proton from that simply hops to another water molecule, and then this proton hopping, what's called the Grothuus proton hopping mechanism, occurs. And because there's no actual physical migration, because it's just the hopping of these protons, the conductivity is actually much, much stronger. The movement of these protons, the hopping of it, is much, much faster than the actual physical migration of the ion. But the H+ ion has no electrons, and so the only way that we can form a bond to it is from a species that has a lone pair. We're going to form a dative or a coordinate covalent bond. So to form the H3O+ ion, we have our H2O molecule, our water molecule with two lone pairs. One of those lone pairs is used in a dative coordinate bond, donating both the electrons to the H+ ion. And so in aqueous solutions, the hydrogen ion is always bound to at least one water molecule, for example, H3O+. However, in equations, quite often it's just written as H+ for simplicity, but it's important to realise that it never actually exists as H+ on its own. So water is actually slightly ionised, slightly dissociates. If we have H2O, we can write an equilibrium reaction where it dissociates into H+ and OH- ions. And we call this the autoionisation of water. Now we can write it like that, or we can write it in a slightly more correct way, which is to write two water molecules reacting with each other, because essentially this is an acid-base reaction. So we have to have one partner acting as the acid, one partner acting as the base. So one water molecule donates a proton, the other water molecule accepts that proton, and so we end up forming H3O+ and OH-. Now essentially there's no difference between those two equations on the left and right, just that the right is a more correct way to write it, and we're also showing that the H+ doesn't exist as H+, but as H3O+. And this equilibrium is established in all aqueous solutions. And so because it's an equilibrium, we can write an equilibrium expression. Remember that when we do this, we always put our concentrations of our products divided by the concentration of our reactants. So the equilibrium constant here, Kc, for this reaction, is our H+ concentration, our OH- concentration, divided by our water concentration. However, in aqueous solutions, as we said, water is slightly ionised. This ionisation is actually very, very small. And so the concentration of unionised water, H2O, is much, much larger than the ions. And it's assumed to be constant throughout any reactivity. So we actually incorporate this, because that's a constant, we can incorporate it into our equilibrium constant. And so essentially how we do this is we just times both sides of the equation by the concentration of H2O. And this gives us a new expression. Kw equals the concentration of H+, the concentration of OH-, where Kw is just the original Kc times by the concentration of water. And Kw is something we call the ionic product of water. And at 298 Kelvin, it takes a value of 1 × 10⁻⁴ mole squared decimeter to the -6. Now that unit has just come from the fact that we've times two concentrations together. Remember that concentration is always measured in moles per decimeter cubed. Timesing two of them together gives us mole to the power of 2, decimeter to the power of -6. And since each water molecule dissociates to one H+ and one OH- ion, in pure water at 298 Kelvin, the concentration of OH- ions must be equal to the concentration of H+ ions. So we can rewrite our Kw expression just using H+, and so therefore Kw equals the concentration of H+ squared. Now, since we know that Kw at 298 Kelvin takes the value of 1 × 10⁻⁴, we can actually work out what our hydrogen ion, and also by the fact that they're equal, the hydroxide ion concentration is at 298 Kelvin by simply taking the square root of both sides. And in doing that, we end up with a proton or a hydroxide ion concentration of 1 × 10⁻⁷ moles per decimeter cubed. Now Kw is a constant at a stated temperature. And because it's a constant, if one component of it increases, the other must decrease by exactly the same amount to keep it constant. So if our proton concentration increases by X amount, our hydroxide ion concentration must decrease by the same amount. So how acidic a solution is depends on the concentration of protons, and we measure it using the pH scale. And we define our pH scale, we define pH to be equal to the negative log base 10 of the hydrogen ion concentration, where our concentration is in mole per decimeter cubed. Now the reason that we use a logarithmic scale is because it avoids us using really small, awkward numbers that are awkward to write and awkward to conceptually think about. For example, a concentration of 1 × 10⁻⁴ moles per decimeter cubed, that would be awkward to think about, and a bit more awkward to write. However, if we used a logarithm to the base 10 of that number, well, log to the base 10 of 1 × 10⁻⁴ is simply -12, a much easier number to think of. The reason why we use a negative log is if we do a negative log, that means that our pH scale is positive numbers, because the log of any number less than 1 is a negative number itself. And there's two takeaway features from this. The first is that the smaller the pH, the greater the hydrogen ion concentration. A pH of 1 has a much greater hydrogen ion concentration than a pH of 10. The smaller the pH, the more acidic the solution is. And the other is that one pH number difference is actually a tenfold difference in hydrogen ion concentration. So a pH of 1 versus a pH of 2 might only be a difference of 1 on the pH scale, but it's a difference of 10 in the hydrogen ion concentration. It's 1 times 10 to the minus 1 versus 1 times 10 to the minus 2 mole per decimeter cubed concentrations. And so if we return to the fact of our pure water at 298 Kelvin, we have our H plus concentration being 1 times 10 to the minus 7, and so the pH, using that equation, minus log to the base 10 of hydrogen ion concentration, the pH of pure water at 298 Kelvin is 7. Now when we give pH values, we always have to give them to 2 decimal places. The pH is 7.00. Now the equilibrium of this water ionizing is endothermic in the forward direction. And so the value of Kw actually increases with temperature. If we go back to our Le Chatelier's principle, if I increase the temperature, the equilibrium is going to want to move in the direction that opposes that change. It wants to move in the direction that's going to take the heat in and return the system to its normal temperature. That's the endothermic direction, the forward direction. And so we end up producing more H plus and OH minus ions at higher temperatures. So actually that means that the pH of water is different at different temperatures. However, it's still neutral, because when we define a solution as being neutral, what we mean is our H plus and our OH minus ions concentration are equal. So for example, at 100 degrees Celsius, when we boil water, it's actually that the pH of pure water is 6, not 7. Now, all that means is that we have a greater concentration of H plus ions, but it's still neutral. Neutral means that the concentrations of H plus and OH minus ions are equal. So we can measure pH by using indicator paper or a universal indicator. That's less precise. A more precise way to do it is by using an electronic pH meter that you've calibrated. But pH also measures alkalinity as well as acidity, because as we said, as H plus concentration goes up, OH minus concentration must go down. And so at 298 Kelvin, we say that if our H plus concentration is greater than our hydroxide ion concentration, it's acidic and we'll have a pH less than 7. If our H plus concentration is less than our OH minus concentration, that's a basic solution, and therefore the pH will be greater than 7. It's also important to realise that we talk about the pH scale going from 0 to 14, but actually we can go to either side of that. We can have pHs that are higher than 14, for example 15 and 16. This is where we have our H plus concentration being smaller than 10 to the minus 14. And conversely, if we have H plus concentrations that are greater than 10 to the 0, i.e. 1, we can end up with negative pHs, pH of negative 1, negative 2, for example. And you can also see at the bottom right the table there of the temperature, the value of Kw, and then the pH of pure water. And you can see that as the temperature increases, for pure water, the pH decreases. It becomes more acidic because we're having more H plus ions because that equilibrium is shifted right. Now we can work out the concentration of protons in aqueous solutions as long as we know the pH. So for example, if an acid has a pH of 4, we have our equation. The pH is the negative log of the H plus ions. So 4 equals negative log of H plus concentration. We can move our negative over to the other side just to make it look a bit nicer. So we have negative 4 equals log of H plus concentration. And now we take something called the anti-log. Essentially, we're going to take both sides and do 10 to the power of whatever is on each side. If we do 10 to the power of log of H plus, that simply gives us the concentration of H plus, the log, the base 10, and the 10 to the power cancel each other out. And if we do 10 to the power of the minus 4, well, that's the equivalent of 1 times 10 to the minus 4. And so we can say that our hydrogen ion concentration, our H plus concentration, is equal to 1 times 10 to the minus 4 moles per decimeter cubed. If we want to find the OH minus concentration for bases, then we have to have an extra step involved. The first step is exactly the same. So if we have a pH that is equal to 11, we're going to use exactly the same procedure as above. So we have minus 11 equals log of H plus, and so therefore our H plus concentration is 1 times 10 to the minus 11 after we've taken the antilogs. Now that's our H plus concentration. If we want our OH minus concentration, we're going to use the fact that we know that Kw equals 1 times 10 to the minus 14 at 298 Kelvin, and we have that Kw is equal to H plus OH minus. So we have our H plus concentration, we have the value of Kw, and so we simply rearrange that equation to give us that our hydroxide ion concentration is Kw, 1 times 10 to the minus 14, divided by the acid concentration, the H plus concentration. And when we put those numbers in, we find that we have an OH minus concentration of 1 times 10 to the minus 3. Now, we can define acids as either being strong or weak. A strong acid is an acid that fully dissociates. Essentially, the equilibrium lies completely to the right. So an example of this would be hydrochloric acid. HCl exists as H plus and Cl minus. The equilibrium is completely to the right. It dissociates into its ions. A weak acid is an acid that only partially or only slightly dissociates. And so the example here is ethanoic acid, associating into the ethanoate ion and H plus, and the equilibrium actually lies quite far to the left. There's very, very little dissociation of those ions. But if we have strong acids, we can work out the pH of a strong acid very, very easily, just using the pH formula. So for example, if I have 1 mole per decimeter cubed HCl, my H plus concentration, because our acid fully dissociates, when we say 1 mole per decimeter cubed HCl, we can take that to mean that the concentration of H plus is also 1 mole per decimeter cubed. So whatever the concentration, if it's a strong acid, whatever the concentration of the acid is, it's also the concentration of the H plus ions. So our H plus concentration is 1 mole per decimeter cubed. So we use our pH expression, minus log of H plus. We do the minus log of 1, and that gives us a pH of 0. And remember to give the pH to 2 decimal places, so 0.00. If I have 0.2 mole per decimeter cubed HCl, again, that means essentially that H plus is 0.2 moles per decimeter cubed because it's a strong acid. The HCl concentration is the same as the H plus concentration. And so using the pH formula again, we now get a pH of 0.63. We can also define bases in the same way. Strong bases fully dissociate, strong, weak bases are partially dissociated. And so again, if we want to find the pH for strong bases, we have to have an extra step required. So if we have a 1 mole per decimeter cubed solution of sodium hydroxide, that means that our OH minus concentration is 1 mole per decimeter cubed. Our OH minus concentration is exactly the same as whatever our base concentration is. And we're going to use the fact that, again, we know that Kw at 298 Kelvin is equal to H plus OH minus and is equal to 1 times 10 to the minus 14. So again, we rearrange that expression now to give us our H plus concentration, plug in the numbers, and we find that it's 1 times 10 to the minus 14 in this case. Now we have an H plus concentration, we can work out the pH. So we simply use the pH formula minus log of H plus, and we get that our pH for this is 14.00. Now, a really important thing to note is that strong and weak in these terms only refers to the extent of dissociation, not the concentration. So strong means it fully dissociates, weak, it partially dissociates. It doesn't have any bearing on actually how concentrated a solution is. So it's very possible to have a very dilute solution of a strong acid, and likewise a very concentrated solution of a weak acid. The strong and weak only actually refers to how dissociated it is. So, time to have a go at a few questions. If you want to have a go, pause the video and the answers will be on the next slide. But we have lots of questions here. So the first is to find the pH of a solution of nitric acid, to find the hydrogen ion concentration for a sulfuric acid solution, to find the pH of a sodium hydroxide solution, and then a couple of questions to do with acids and bases at the end. So pause the video and have a go, and the answers will be on the next slide. So the first question asks us to find the pH of a 1.75 times 10 to the minus 3 mole per decimeter cubed solution of nitric acid. Now, nitric acid is a strong acid, so the equilibrium of the dissociation of HNO3 into H plus and NO3 minus lies entirely to the right. It's a strong acid, it's fully dissociated. So what that means is our concentration of HNO3 is equal exactly to the concentration of H+. So we can simply use our pH formula minus log of H+ to give that our pH is equal to 2.76. And again, remember to give it to 2 decimal places. The second question asked us to find the hydrogen ion concentration for a sulfuric acid solution that has a pH of 2.7. So this essentially is the reverse of the question we've just done above. The important thing to note here is that sulfuric acid is a strong acid. The dissociation of H2SO4 into 2H plus and SO4 2- lies completely to the right. But that sulfuric acid is a diprotic acid. That means that it releases 2 H+ ions per mole of H2SO4. So we have our pH is equal to the negative log of H+. To find our H+, we need to take anti-logs of both sides. We need to do 10 to the power of both sides. And so when we rearrange our equation, we get that H+ is equal to 10 to the minus pH. So in this case, H+ is equal to 10 to the minus 2.70. This gives an H+ concentration of 2 times 10 to the minus 3 moles per decimeter cubed. Now for a normal monoprotic acid, this would be the end of the question, but the important thing here is that sulfuric acid is a diprotic acid. It releases 2 H+ per molecule of sulfuric acid. And so therefore, to actually find out what our sulfuric acid concentration was, we have to divide that concentration of protons by 2. So our concentration of sulfuric acid was actually 1 times 10 to the minus 3 moles per decimeter cubed. The third question asked us to find the pH of a 2.16 times 10 to the minus 3 mole per decimeter cubed solution of sodium hydroxide. Remember that if we want to use it to find the pH of bases, we have to use the extra step and use our Kw. So we know that Kw is H plus OH minus concentrations and is equal to 1 times 10 to the minus 14 at 298 Kelvin. So we're going to rearrange that equation to find H plus concentration, it's Kw over OH minus, put the numbers in, and we find that our H plus concentration is 4.63 times 10 to the minus 12. Then simply, now we have H plus, we can put that into our pH expression, and we find that our pH is 11.33. Question 4 then talked about lime scale, which was calcium carbonate being removed using acid cleaners. So to write the equation for limescale reacting with HCl, so remember the general formula that we have a carbonate plus an acid is going to give us our salt, water and carbon dioxide. So calcium carbonate reacts with HCl to produce calcium chloride, water and CO2, and then it's just a case of making sure that everything's balanced by putting a 2 in front of the HCl. And then we knew that bleach cleaners contain chloric acid, HClO, and why we shouldn't mix acid and base-based bleach cleaners together. And the reason for this is because your acid-based cleaner is your HCl, your bleach-based cleaner is HClO. If you write the equation for those two reacting together, you form Cl2, chlorine, and water. And the problem is that chlorine is very, very toxic, so you wouldn't want to do that. So thank you for watching. You can find lots more videos like this on my YouTube channel. I hope you find it helpful. If you have found it helpful, then please consider leaving a review on my one of my tuition websites. I offer online tuition for chemistry. If you'd like to get in contact with me about that, you can do. And if you need any more help with your chemistry, you can always feel free to drop me an email.